So, we had A and I think I had B here and I had taken an orbit. So, this is A, this I am calling C1 and this I am calling C2, right. So, if you go by the previous method, the faults are A0 and A1, B0 and B1, C1 0 and C1 1, C2 0, C2 1, right. And between these two maybe we can go ahead and eliminate one of them because it is an AND gate. So, try to generate a test vector for let us say, let us start with C1 stuck at 0. Okay. So, C1 stuck at 0, we will have to activate the fault by placing A equal to 1. Okay. So, A equal to 1 is required to activate the fault. So, that will produce a 1/0 here. A good circuit will have a 1, a faulty circuit will have a 0 and this will become 0/1, right, and this will have a 1/1 because both the good and the faulty circuit will have a 1. And in order to propagate this guy I have to put it 0 here. So, I will put a 0 here. Okay. So, that will cause 0/1. Okay. So, C1 stuck at 0 can be found by 1 0. Now, let us try C1 stuck at 1. So, here so we have C1 stuck at 1. To activate it we have to give a 0 here and that will cause a 1 here, a 0 here and 0 comes here. So, this is x. Okay. So, this is and a good circuit will produce a 1. So, this is 0x. So, either 0 0 or 0 1 will catch. Okay. Next, let us try to do C2 stuck at 1. So, C2 is stuck at 1. So, we have to activate it by putting a 0 here, right, and then we have to propagate it further by putting a 1 here. So, this is 0/1 and by propagating it we will make it 0/1 here also, right. This 0, this there is no fault on this line. So, this will come and become a 1 and now you see there is something interesting happening here, this output became 1. Okay. So, the output is 1 no matter what. The fault got propagated to this point, but I am not able to propagate it to the output because this 1 is, I need this 1 Okay, I mean the reason why I got a 1 here is because this 0 is required for fault activation. This 0 is required to activate this fault, but unfortunately this 0 also causes a 1 here, which prevents it from propagating to the output. So, there is a conflict, right. That means we are not able to detect, we cannot have a test for C2 stuck at 1. Okay. So, that means we cannot assume that all tests, all faults can be detected. The reason why this is happening is, look at the output. Okay, if this is A and B, and let us say I call this G. What is G? G is nothing but A bar plus AB. The A bar plus AB can be simplified. You may have learned this in your digital class. A bar plus AB is same as A bar plus B. So, this AND gate, there is a redundancy. So, we did not really need that AND gate at all. Okay, we could have directly got it like this: A bar, B. So, as a result, the input at that AND gate, there is no test. So, something that you have to understand. So, redundancy in circuits, we try to eliminate redundancy, right, when we do Karnaugh maps, etc., right. See, there may be a Karnaugh map like this. I may have a 1, 1, 1, 1. So, let us say this is A bar A, B bar, C bar, B bar, C, BC and BC bar. Okay. How do I minimize this Karnaugh map? So, we might use these two and these two. Okay. So, the output is let us say G, this is A bar B plus A C. So, it looks like this: A bar B, this is A bar B and then AC. Then X. So, what is happening here in this square, the input is 0, 1, 1. Okay. So, if I apply a 0, 1, 1, I will get a 0 here, and wait, 0, 1, 1. I am sorry, this is 1, right? Yeah. Excuse me. Okay. So, this is a 1 and I get a 1 here, and I get a, this 0 is here, and I get a 0 here, and I get a 1. Okay. So, I got a 1. Now, when it comes to this input, A is 1, right, and B is 1. and C is 1. So, A changed from 0 to 1. When that happens, this should go from 1 to 0, this should go from 0 to 1, right, and this should go from 1 to 0, and this should go from 0 to 1, and the output should remain 1 to 1. Okay. So, 1 to 0 transition and 0 to 1 transition, if they happen at the same time, okay, and these changes also happen at the same time, then the output will remain at 1. Okay, the output will remain 1, but that is unlikely to happen, right. It is possible that this 1 to 0 transition may take some time, okay, because there is a gate delay involved. Okay, it may take a little time, right. Meanwhile, so there is a small chance. See, everything has a delay. The interconnects have delays, the gates have delays, right. So, it is really difficult to control that these two changes, okay, happen at the same time. We are expecting the OR gate inputs to go from 1 to 0 and 0 to 1 at the same time. Okay. Any delay here, see, suppose this input, suppose I have this input, let us say it is happening a little sooner, okay, and the 0 to 1 transition is happening a little later. So, there will be a small period where the inputs of the OR gate will be 0, and as a result I will see a small glitch like this. Okay. So, this is the we call this as a hazard. It may happen. We may be lucky and both the transitions happen at the exact same time, but there may be a small chance that these do not happen and we may get some sort of a intermediate glitch. Okay. So, some people include a third term. Okay. So, they will add a BC term, okay, another term BC. What is the advantage? See, in this, remember that B has remained same and C has remained same. So, the OR gate will continue to see a 1 here through this blue OR gate. So, it will not glitch, it will remain, it will hold to that 1. Okay. So, sometimes to prevent this kind of glitching, people may include an extra term. Okay. This term, the blue term is not required. So, in your college digital design class, you may have been told not to include such terms because it is extra logic. It is more expensive to unnecessarily add an extra term. But there is some advantage in adding that extra term. So, this eliminates this hazard. But the disadvantage of having that extra term will be that some faults cannot be tested. Okay. So, redundancy results in some untestable faults. So, one of the reasons for some faults being untestable, okay, is this as well.